For centuries, physicists searched for a single framework to explain the universe. From Newton's laws to Einstein's relativity and the mysteries of quantum mechanics, one question remained: what is the ultimate fabric of reality? Out of this search was born a bold idea: string theory. In the 1950s and 60s, particle physics was in chaos. New experiments revealed an overwhelming number of subatomic particles, a so-called particle zoo. Scientists sought order, a pattern to tame the chaos. The first attempts came through symmetry principles and the S-matrix theory, pioneered by physicists like Geoffrey Chew, who proposed that particles might not be fundamental at all. In 1968, Gabriele Veneziano, an Italian physicist working at CERN, wrote down a mathematical expression to describe the strong nuclear force. The formula worked astonishingly well, but no one knew why. Soon, researchers realized that this formula looked like the scattering of vibrating strings. This was the birth of the idea that particles could be tiny strings. Physicists began exploring the strange possibility: what if the fundamental building blocks of nature were not points, but one-dimensional strings vibrating in multiple ways? Different vibrations could correspond to different particles, like musical notes on a violin string. At first, the theory seemed to describe only the strong force, but it contained something unexpected: a massless particle with properties of the graviton, the particle of gravity. By the mid-1970s, the strong nuclear force was better explained by a new theory, quantum chromodynamics, part of the Standard Model. String theory fell into obscurity. Yet, a small group of physicists noticed that strings naturally included gravity. This realization changed everything. Perhaps string theory was not about the strong force, but about unifying all of physics. In the 1980s, string theory returned as superstring theory. It combined strings with supersymmetry, a deep connection between particles of matter and forces. To work consistently, the theory required 10 dimensions of space-time, far beyond the familiar 4. These extra dimensions, theorists suggested, might be curled up so small that we cannot see them. The mid-1980s became known as the first superstring revolution. Hundreds of physicists joined the effort. For the first time, it seemed possible that string theory could unify gravity with quantum mechanics, solving a problem that had resisted all attempts since Einstein. But string theory was not finished evolving. In the 1990s, Edward Witten and others showed that 5 different versions of string theory were all connected. They were pieces of a larger puzzle called M-theory, involving not just strings, but higher dimensional objects known as branes. The vision of reality grew richer, a universe woven from vibrating strings and membranes in multiple dimensions. From a simple formula in 1968 to a vast framework of mathematics and physics, string theory has become the leading candidate for a theory of everything. Though untested by experiment, it continues to inspire generations of scientists, offering a glimpse into the possible ultimate architecture of the cosmos. The origin of string theory is not just a story of physics, but of human curiosity, the endless quest to understand what reality is made of.